Okay, this is the second lesson, AQA AS Redox lesson 2. You need to use your textbook. This lesson corresponds to pages 158 to 159. If you haven't watched it already, you should watch AQA AS Redox lesson 1 before you start this. Okay, so here are today's lesson objectives. First of all, you need to define what an oxidation state is, and then you need to be able to calculate oxidation states. Okay, so let's take the first one of those. So first of all, you need to define an oxidation state. And the official definition of oxidation state, if you look in the back of your textbook, is that it's the number of electrons lost or gained by an atom in a compound compared to the uncombined atom. And this forms the basis of the way of keeping track of electron transfer reactions. You sometimes see this called the oxidation number. So that's the exam board definition. I find it easier to think about it in a slightly different way, which I'll show you on the next slide. So another way of looking at it is that the oxidation state is a number of electrons which have to be added or removed in order to become neutral. And this makes sense when we look at a few examples. So I'm going to take you through 3 examples. So for the first one, for magnesium 2+. So if you have an ion at Mg2+, then in order to become neutral, the Mg2+ needs to gain 2 electrons, because it has a 2+ charge, which means it has 2 less electrons than protons. So to become neutral and have the same number of protons and electrons, it needs to gain 2 electrons. So this means because it needs to gain 2 electrons to become neutral, it then has an oxidation state of +2. So a second example, if you take silver as a metal as an atom, it's already neutral. So because it's already neutral, it doesn't need to gain or lose any electrons to become neutral. So its oxidation state is therefore 0. Our third example is then O2-. So the oxide ion O2- needs to lose 2 electrons to become neutral because it has 2 more electrons than it has protons. So in order to become neutral and have the same number of protons as electrons, it needs to lose those 2 electrons. So the oxidation state of O2- is then -2 because it needs to lose 2 electrons to become neutral. So hopefully you can now have a definition of the oxidation state and be able to easily identify the simple ions. Now there are several rules that we need to be able to remember in order to calculate oxidation states. So the second thing we need to do is to be able to calculate oxidation states. So there's a series of rules that we need to do this, and these are on this slide. So the first one is, if you have a molecule, then the sum of the oxidation states of all the different elements in that molecule have to add up to 0. If you have a complex ion, so a complex ion is just an ion that's got more than one element. So lots of these you've come across before. So for example, SO4(2-), you'll have come across before. That's a complex ion. It's got sulfur and it's got oxygen, and the overall thing has a charge. So it's therefore a complex ion. So the SO4(2-), because it's a 2- ion, then the sum of the sulfur and the oxygen has to add up to the 2- charge on the ion. Okay, now by looking in the periodic table, you can see what the normal numerical value of the oxidation state is. So if you have a metal, for example, then it will normally have a positive oxidation state, and it will normally have the numerical value of the oxidation state will normally be what's the group number of that metal. So if you have a group 1 metal, such as sodium, sodium forms a +1 ion, so it's normally Na+. So sodium will then have an oxidation state of +1. If you had a group 2, such as magnesium, then as we saw in the previous slide, that's an Mg2+ ion, so it would normally have an oxidation state of +2. And then again in group 3, if you had aluminium, Al3+, it would have an oxidation state of 3+. So the metals are very easy, as long as you're not talking about transition metals, and we're not going to worry about them for now. The non-metals are slightly more difficult to remember because it's the other way around, but if you're in group 7, they would normally be a -1. So if you should be used to from GCSE that a group 7 metal will normally form a -1 ion. So in which case, it has got 1 extra electron than it would normally as an uncombined atom. So therefore its oxidation state will be -1. Group 6 will normally be -2, and group 5 normally -3. So there are also some specific rules for calculating oxidation states. So fluorine, I've put these in a specific order, so I put fluorine first because fluorine is always -1. So if you have a fluorine in a compound or a complex ion, it is always going to be -1. And that's because it's a most electronegative element. So it's always going to have a -1 ion. The only exceptions are when you've got a fluorine atom by itself and when you've got a fluorine molecule. So if you have an F2 molecule, and in both those cases, the oxidation state would be 0. But unless it's a fluorine atom or an F-fluorine molecule, then where it will be 0, then it will always be -1. So I've put fluorine at the top of these specific rules because it is always -1. The second one of our specific rules is hydrogen. So hydrogen is always +1 in most cases, but there are two exceptions. Firstly, if you have a metal hydride such as lithium hydride, then hydrogen is then +1 because the metal is more positive. So if you have hydrogen for metal, the hydrogen becomes -1. So if you have lithium hydride, the hydrogen would have an oxidation state of -1. But apart from that, if the hydrogen's in a compound, it's always going to have an oxidation state of +1. Or if it's in a complex ion, it's always going to be +1. As an atom or a molecule, H2 molecule, then it will be 0, just like the fluorine was. But apart from H atom and H2 molecule, where it's 0, and metal hydrides where it's -1, hydrogen is always going to be +1. Our third example of a specific rule is oxygen. So oxygen is always -2, and the exceptions for oxygen are hydrogen peroxide, which is H2O2 if you've not come across that before, and in that case the oxygen is unusual in that it has an oxidation state of -1. In the F2O, oxygen has a +2 because fluorine is always -1. So if fluorine is always -1, you've got 2 fluorines, so that becomes -2. So because it's a molecule, it's got to be neutral, so the oxygen has then got to be +2. And then there's the usual exclusion as well, where oxygen is an oxygen atom or an oxygen molecule, then it's going to be 0. Okay, so there's the specific rules. Now we can do some examples. So the first example should be quite straightforward. Now if you're feeling confident with the rules now, you can pause the video and you can have a go at calculating these oxidation states. If you're not feeling confident, then we'll go through them now as some examples. So the first one, magnesium and chlorine. So this is a really straightforward example because it doesn't actually require any working out because you're just using the rules. So magnesium is in group 2 if you look in the periodic table, so it becomes Mg2+. Chlorine, you should know, is in group 7. So group 7 is going to form -1 ions. So the chlorines themselves will be -1. So the oxidation state of the chlorines will be -1 and the magnesium will be +2. And we can check that we've got this right by making sure that it adds up to 0. So if you've got +2 from the magnesium, and then you've got -2 because you've got 2 chlorines and each one's -1, then that becomes 0. So the molecule overall, although it's ionic so it isn't really a molecule, but the formula unit, we should say, magnesium chloride, is overall 0. Now, water is a molecule, and we said in our rules that hydrogen was always +1, and we said that oxygen was always -2. And we just check that this works. So it's a molecule, so it's overall, if you add the oxidation states up, they should become 0. So you've got 2 hydrogens, so you've got +1 +1, which is +2, and then you've got -2 from the oxygen, so if you add those two together, you get 0. So the overall oxidation state for the molecule is 0, so that's good. Now the next one, we're going to have to do some simple mathematics. So we look at nitrogen, and we've got hydrogen. So ammonia you'll have come across in GCSE when you did that Haber process. So hydrogen, we said from our rules, is always +1. So the hydrogens are going to contribute, there's 3 of them, so they're going to contribute +3 overall to the molecule. And the molecule has to be 0 overall. So if the hydrogen's +3, then the nitrogen has to be -3 in order to make the molecule as a whole 0. So hydrogen becomes +1 and the nitrogen becomes -3. Okay. Now we'll do the last example, which is slightly more complicated because you've got a complex ion. But the process is exactly the same. In the molecule, it had to add up to 0. In the complex ion, it had to add up to -2. So again, from our rules, we know that oxygen is -2. There's 4 of them, so the oxygen has to add up to 8-. So the sulfur makes up the difference between the 8- and the 2-. So whatever sulfur is, when you add it to 8-, it has to come to 2-. So hopefully you can tell from your maths that in order to go from 8- to 2-, you have to add 6. So the sulfur then becomes +6. So the oxygen is -2, but there's 4 of them, so it's 8-. The sulfur is +6, and that will overall give you your -2 charge. Okay, so these were our lesson objectives to be able to define an oxidation state. Hopefully you can do that now. And then we also needed to calculate oxidation states.